Look at that integral. This one's just a design. The design here is to remind you about your cotangents and cosecants, those relationships, and in particular that the derivative of cotangent is minus cosecant squared x. Okay, at this stage in the book, you're required to be a world expert at all things derivative, and they're just reminding you this is one of the ones you're supposed to have in your repertoire ready to go. Now, if you didn't see that, maybe you could turn this into sines and cosines and see if you could do the problem that way. But for now, this is the design. Okay, and again, it's that square root. Wouldn't you love to have square root of u? So if I'm going to have that, well, I would have to pick u to be cotangent x. Then du is minus cosecant squared x dx. And then when I have to substitute for everything I see, I have square root of u from the square root of cotangent x. What's remaining to be substituted for is this, and I've got it right here. This thing is, let's see, cosecant squared x dx is minus du. Okay, so I put my du here and my minus. Okay, and those are essentially equivalent integrals, but I prefer to do this one, much easier for me. So I have minus. Remember, in previous videos, I implored you or requested or suggested that you have this one memorized. You don't want to have to redo it every single time. It's 2/3 u to the 3/2 plus c. I will redo it for you every time, but for your own fluency in this, it's better. Okay, so remember that square root of u is u to the 1/2. So the integral of u to the 1/2 is, it's u, and then you add 1 to the 1/2, but that's 2 plus, it's 1/2 plus 2 over 2, so that's 3 over 2, and then you divide by that very 3/2, but dividing by the very 3/2 is the same as multiplying by 2/3, and that's why I suggest that you just have that memorized, because you don't want to have to redo that every single time, especially in a test situation. Okay. And it comes up often enough. They love to put the square root in there, make you deal with fractions and all that. Okay, 2/3, and then I'm going to put the u in. What was u? It was cotangent. So we have cotangent 3/2 x plus constant. If you look through all these problems, or even, just the ones that have the square root, you see it's kind of a theme. If you just look through the book at the number of questions that have little square roots in them, it's worth it to focus on those, because the odds are it's going to show up on a test or something if that's what you're studying for. Number 36. Oh, by the way, the last one was a red numbered problem. So it's kind of highlighting this cotangent derivative that the author of the book knows that people forget, so he's just putting it back in there for you. Okay, number 36. We've got another derivative that becomes a long-lost derivative. I mentioned this in the previous video. But this is one that people just don't see as often. It's related. It's related to e to the t, right? E to the t prime is just e to the t, the easiest derivative in the history of the world. And e is just 2.718 and so on. I'm not going to try to display any kind of memory tricks or anything, but e is approximately that, right? So why, if that's the easiest derivative in the history of the world, then why is this one so difficult? Because, after all, 2 is almost 2.718. Why should they be so different? Well, the difference is that you need to have the extra goodie for this one. So e to the t, it gives you e to the t back again. 2 to the t gives you 2 to the t back again with the extra goodie ln2. And in fact, this one has a hidden goodie. It's ln e, but ln e is equal to 1. So we just write e to the t. And so it's consistent. But that's the design of the problem, to remind you that there are these other derivatives that we don't see that often, but you once were a world expert at. Okay, now I see the 2 to the t in the bottom and the 2 to the t in the top, and I say this is a great opportunity to pick the denominator to be u. I'm going to pick the whole denominator to be u, thinking to myself, I love the integral 1 over u du. So when you see the derivative of the denominator sitting in the top, that's a 1 over u du situation. You see it's 1 over u and then the derivative of u. So that's what we like, because that's ln absolute value of u plus c. All right, let's do that. So du is going to be, like I said, the derivative of 2 to the t as well as 2 to the t back again, but you got to have the little extra goodie, ln2, and the derivative of 3 is 0, so I have dt here. Almost drew x, dt. Okay, let's substitute for everything we see. On the bottom, I have u by design. On the top, I need to account for the 2t dt, but I have this little extra 1 over, or this little ln2. So 2t dt is equal to du over ln2. If I just bring this ln2 over to the other side. Okay, so I have 1 over ln2. If it bothers you that it's ln2, well, that's part of what you have to do to get good at calculus. You got to get over that. Okay, it looks a little weird, but it's just like a 7. ln2 is just a 7. In fact, you'd rather write ln2 than what ln2 actually is, because it's a big long decimal. So it is better to write it ln2. So try to just get used to it. That's called getting a little mathematical maturity. You run out of things that cause you to have the deer in the headlights moment. And I recognize that that's one of those things right now, the 1 over ln2. Some of you are just going, oh my God, it's ln2 again. Oh my God. Well, we got to get over it. Okay, it's just 1 over 7, same kind of thing. All right, so let's finish it up. I have 1 over ln2 times ln absolute value u plus c. And then I'll put back what u is, so I put it in the form that the problem was given to me in. So ln absolute value 2 to the t plus 3 plus a constant. There you go. Now I didn't look. What number is this? This is, oh, it's number 36. You won't have the answer in the back of the book. But this one here, if they had it in the back of the book, it would not have absolute value, because 2 to the t is always greater than 0. And so 2 to the t plus 3 is also always greater than 0. And therefore, you don't need the absolute value. So ln of 2 to the t plus 3 is actually equal to ln of parentheses 2 to the t plus 3. And then what happens here is you get the problem all right, and you have your absolute values, and you're all proud of yourself that you remembered that. And then you go to the back of the book and you look at it, and it doesn't have parentheses, and you go, oh, is that a typo? What's going on here? Did I get it wrong? I thought I was supposed to have that. Okay, anyway, in this case, the absolute value is doing nothing. It's like dribbling between your legs when nobody's guarding you. So the absolute value might as well not be there, but it is there, so I'm leaving it in. But if you were to look it up in the back of the book, it wouldn't be there because it's an even number. But if it was an odd number, then the answer would be presented like this. Okay, anyway, that's a lot of nothing. Number 37. That's live stream, so I'm not allowed to take that out. So you gotta endure it. It's part of the price of listening to me do math. Okay, here we go. The famous hyperbolic trig functions. famous only because people just know that they exist from seeing them in their calculus book, but they never study them because all the calculus classes in the history of the world always skip this section. And if you're in engineering, you may use them, just for your classes, so you get used to them. But nobody ever does this section. So this is a reminder of the material that you became a world expert at, but nobody ever studied that section. So I got to do it a little bit. Okay, and I'm not going to dwell on it too much, but SINH is said sinh, and it is defined to be the function e to the x minus e to the minus x over 2. And why it's defined that way and why it's related to sine is for another lecture. Let's just go with, this is what it's called. This is the definition of sinh, or hyperbolic sine. Okay, and then cosine, or cosh, hyperbolic cosine, is e to the x plus e to the minus x over 2. They are very similar. Why cosine and sine are related to e to the x is also for another lecture, but that's a good question for you to go and investigate yourself. What the heck does e to the x have to do with sine and cosine? Well, they are intimately related, and this is an example of why they chose this notation. Okay, well, we're interested in derivatives and antiderivatives, right? So we want the thing whose derivative gives us this. And that looks pretty messy, and I don't think I want to put all the e to the x's in, but I could. But I'd have to square it and, FOIL and all that stuff. So what we're going to do is we're going to do a little side work because the book expects that to have been done. So what is the derivative of sinh? It's the derivative of e to the x over 2, which is just e to the x over 2, and then minus the derivative of, let's write that out, actually, what I just said. When I say let's, I mean me. So the derivative of this thing here is the same as the derivative of e to the x over 2 minus the derivative of e to the minus x over 2. See, I just break that up into two fractions with my mathematical sledgehammer. And then when I do these derivatives, the derivative of e to the x is just e to the x. I just get e to the x over 2. And then here I have to be a little careful because I have a minus, but then on the inside I get the derivative of that term, e to the minus x over 2, is minus e to the minus x over 2. And so then that gives me e to the x plus e to the minus x all over 2, which happens to be the hyperbolic cosine. Look at that. And so the derivative of sinh is cosh, which matches up with derivative of sine is cosine. Okay, so let's condense that. We have derivative of sinh is cosh. And then let's do the same thing over here. Let's just do it over here. So cosh, the derivative of cosh is the derivative of e to the x over 2 plus the derivative of e to the x, e to the minus x over 2. Derivative of the first term is just e to the x over 2. Derivative of the second term is minus e to the minus x over 2, because the derivative of e to the minus x is e to the minus x back again times the derivative of negative x, which gives you that minus out in front. Okay, and then that's e to the x minus e to the minus x over 2. Which is sinh. Okay, and then you'll find that in section, I'm just looking it up here for you. This is in section 3.11, and it is on page 259. And this is section 311, page 359. Okay, if you want to go look that up yourself in the book. Okay, anyway, here's what we found out, is that the derivative of sinh is cosh, and the derivative of cosh is sinh. And unfortunately, it's not minus sinh, because that would be easier to remember, because derivative of cosine is negative sign, but no, they are both positive. Okay, so now let's get back to the integral that we have here, now that we have that knowledge. And the integral that we had is, without scrolling up here, I have sinh squared cosh dx. Okay, now we've seen this a bunch, right? When you have a glom of something and then you have its derivative sitting here, here's the glom because it's a squared thing. And then you have its derivative sitting there. A good thing to pick is the thing inside the glom. Remember, sinh squared is the same as sinh quantity squared. Okay, so there's a little parentheses hidden there. Pick the thing inside the parentheses. I'll pick u equal to sinh. Then du is sinh x, excuse me. Then du, we've already done our work up here, so the derivative of sinh is cosh. And there it is sitting there. See how rigged it is? And then the derivative here is u squared, or sorry, the integral transforms into, I have sinh squared, but u is equal to sinh, so I have u squared. And then what I have to substitute for is this cosh x dx, and I've got it perfectly there as du. So that's u cubed over 3 plus a constant, and then I can put in the original u, and that gives me sinh cubed x over 3. There you go. Oh, we had to go a little bit into the weeds there to do the sinh and the cosh. Lucky for us, they only had one of those in that whole section, just to make you go back and look at that, or go look at it for the first time. Okay, number 38. As the integral gets more and more complicated, that you should expect it to just be more and more rigged. They have to be built a certain way, otherwise you can't do them. This section is on undoing the chain rule, essentially. That's what U substitution does for you. It simplifies it so you don't have to deal with the chain rule when you're undoing the derivative. And so it has to be presented in the way that has that chain rule already in there. And this is an example, but boy, they worked really hard to get this confusing. So another way to write this, and the reason why I do this is because you say, I see a tangent here, and then I immediately say to myself, well, if I'm going to pick u to be the thing inside the square root, well, then I'm going to get secant squared as my derivative, and I don't see that there. But oh wait, oh shoot, 1 over cosine squared t, that's equal to secant squared. Wouldn't it have been nice if they just put that in there for us? They just little too much confused the enemy for my taste. So this integral could have been written as secant squared t dt over square root of 1 plus tangent. And if tangent t, oh, look at that, I did it in both cases. Look at me having a consistent projection on my part here, just wanting it to be x. We all want it to be x, makes us feel at home. But no, we're going to do this in t, the way that it was presented. All right, so 1 plus tangent t is what I want to pick for u, because I love having 1 over square root. I know I can do that. 1 over square root of u is doable for me. But you see how they hid it from us? It's really secant squared there. So I'll pick u equal to 1 plus tangent t. Then du is derivative of 1 is 0. Derivative of tangent t is secant squared t dt. Substitute, which is also equal to dt over cosine squared t. So this integral is exactly 1 over root u times du, because the thing I have left over to substitute for is right here, and that's exactly equal to du. Okay, this is another one that I suggested that you have memorized, so you don't have to deal with the fractional exponents, but I'll do it for you. So 1 over u, this is the same, let me just write it, u, square root of u is equal to u to the 1/2, so the integral of square root of u du is the integral of u to the 1/2 du. Then I have to add 1, which is the same as adding 2 over 2 to get, oh, sorry, this is negative, and I want 1 over, and I want 1 over. Look at this live stream here. Okay, I'm fixing it. Let me just recap what I did to fix that. Okay, I wrote root u instead of 1 over root u, but I meant to write 1 over root u, so I'm fixing it. Okay, so I have 1 over root u, and then that's u to the negative 1/2. That's the integral I'm doing. And so when I add 1 to negative 1/2, I'm adding 2 over 2, so that gives me u to the positive 1/2. Then I have to divide by that very 1/2, which is the same as multiplying by 2, because it's the reciprocal of 1/2. And that's why I suggest that you just memorize it. Okay, the antiderivative of 1 over root u is 2 root u. Then you don't have to redo that every single time. And I'll say that every single time because I don't know if you've seen previous videos, so I just keep doing that every time. So I apologize if you watch all the videos and you keep seeing me do that. But that's the way it goes. Okay, now we're done because I'm going to put in the 1 plus tangent t. You see how I just didn't want to write tangent t because it already had a t in it, the tangent. I don't like that variable for t. Okay, there we go. You see? Now mentally take that derivative and see that you get back to what we started with there. See, it's 1 over, it'll be 1 over 2 root 1 plus tangent t, but we have the 2 in the top, so those will cancel, times the derivative of the inside, which is secant squared, which can also be written as 1 over cosine squared. Moving on. Now, this is fun. This is a pair of questions, 39 and 40. This is what they do to you. This is what your instructor, whoever it is that you're taking this class with, this is how they can get you. Right here. So I'm going to put both of them up at the same time, and then we'll just do one at a time. But I want you to just compare them because they're put next to each other in the book for a reason. And it's good to just see how close they can be and how they have different solutions. Okay, you can just sit there and ponder that. Pause the video and ponder those two. I've got sine 2x there and sine x. Now, for the student who is really fluent with this stuff and maybe just took trig last year and are just going right into calculus, or you're just really into this, then you're going to recognize this sine 2x. This is one of these identities that we get when we take trig and also in calculus. So let's remind ourselves of that because that's the design of the problem. We're supposed to realize, we're supposed to look at this sine 2x and have this knee-jerk response and say sine 2x is 2 sine x cosine x. Naturally, you would do that, right? Well, if you're dealing with math a lot, this does come up, and so that's the design of the problems, to remind you of this identity. Okay, so we can write it that way to start, or we can say to ourselves, well, what would we like to have here to make this problem doable? Well, I see a cosine and I see a sine. I mean, I'd love to pick the denominator to be u, and then I'd have 1 over u du. Wouldn't that be great? But it doesn't look like, when I look ahead in my mind, it doesn't look like that'll work out. But let's just try it. We'll follow our nose anyway, and we'll see that it does work out. So u plus cosine squared x du is 0 from the 1. Derivative of 1 is 0. And then the derivative of cosine squared is 2 cosine x times the derivative of cosine, which is minus sine x dx. And then we can do a little housekeeping. That's negative 2 cosine x sine x. And look at that. See, it always comes in this form where the sign comes first when they present the identity. And then in the integral, it comes out like this. You don't get that trigger because you're used to seeing the sign first. But anyway, this is the same as minus 2 sine 2x if you're fluent with your identities. That's the design of the problem. You may think that's playing unfairly, and I think I would agree a little bit, because if somebody doesn't know that, you basically just hit a dead end. Okay, well, now that I see that, then I can do my substitution here. This integral here, let's re-show it. So I have sine 2x over 1 plus cosine x. On the bottom, I have 1 over u, because I picked u to be that. And then on the top, I have, well, it's minus. This thing here is the same as, oh, excuse me, I put an extra 2 in there. That shouldn't be a minus. That should just be, that should just be a minus, not a 2. See, if I had a live stream, my chat would just blow up, and then we'd fix that right away. Because the 2 is incorporated. This part right here is sine 2x. Okay, so anyway, the integral converts into 1 over u du. So then that's minus ln absolute value of u plus c, and then I can put back what u was. U was 1 plus cosine squared x. And again, that's another one where, so here's my final answer. But when you look in the back of the book, which I haven't done, and I'm not gonna, but I just predict that they will not have the absolute value because cosine squared is a positive number or 0, and so 1 plus it is always positive, and so therefore you don't need the absolute value. It's not doing anything except causing anxiety. But what really causes the anxiety is when you look at your answer and then you look at the back of the book and they write it this way. That'll really cause you some anxiety. Okay. That is an odd one. Okay, I mean an odd numbered problem, so it's in the back of the book. You can check that for me. And then put it in the comments if I got it wrong. Oh my God, what a scandal. All right, number 40. So let's do that. Let's do this one right after it. This one only has sine x at the top, in the top, and I still have the same 1 plus cosine squared x. And so you might say to yourself, okay, let's do this incorrectly, as if I'm you and I'm just trying stuff. Don't be afraid to do this. Okay, this is the wrong answer, but let's do what we did before and see how it doesn't work. U equals 1 plus cosine, because you say, oh, I just love that 1 over u. I want to have that one, so let's just see if we can make it happen. So you start down that road. Okay, 1 plus cosine squared t, and then du is 2 cosine t sine t. And you go, darn it. I don't have a cosine. I don't have a cosine somewhere else in the problem. I'm just going to get stuck here when I try to substitute for everything. You see? So we'll give up on that. And then you remind yourself, oh yeah, whenever I pick u to be cosine, well, du is sine, right? So let's try that. Even if you don't see where this is headed, try some things. So if I let u equal cosine, well then du is minus sine x dx. And then this oh my gosh, look how rigged it is. Well, see, you have to be careful. That doesn't mean I replace the whole denominator. See, I don't have the 1 in there, so it's 1 plus u squared in the denominator, and see if that triggers anything for you. And then I have the sine x dx to substitute for. Well, that's going to give me minus. We can bring the minus over, and we get minus du. So I have a minus, and I have du there. In fact, let's write it like this so that it helps the mind see what the answer is. Okay. Now, what is supposed to happen if you're a calculus student studying this book all the time and you know every little nuance to the book, you're supposed to recognize this as the derivative of inverse tangent. You see? So there we go. This is equal to inverse tangent u plus c. And then I have inverse tangent. I got to put what u is. U is equal to cosine plus c. There you go. Okay, so those are good to do right together, the way they put them in the book, just to see that they can look very similar but have very different solutions. Okay, that was number 40. Oh boy, here we go. Number 41. Number 41. Here we go. We got the integral of cotangent x. Wouldn't you want to be able to do the antiderivative of all the trig functions? There are 6. We know how to do sine. We know how to do cosine. Do we know how to do tangent? Do we know how to do cotangent? Do we know how to do secant? Do we know how to do cosecant? We don't yet, but here we go. We're about to find out. And in fact, I believe, without looking, I'm going to look right now, but I think maybe they do tangent as an example. Yes, they do. Example 6 is tangent. So see example 6 in the book for the integral of tangent. So they're thinking, okay, well, you did example 6, and now you're ready to do number 41. That's what the authors are thinking. I don't know that that's what they're thinking. And I can't ask him because I think he's dead. So he left us this great calculus book, Mr. Stewart. Okay, let's do this. So here we go. This is hidden. There's nothing to pick for x. And let's just do that for some of you. Some of you say, well, I'm going to pick u to be x. Well, let's do that. U equals x, and then du is equal to dx. And then I convert this integral into cotangent of u du. And I haven't done anything except just change the variables. So no, that's not going to be anything. And that leads us to the problem of what do we do? Because if we pick u to be cotangent x, well, then du is minus cosecant squared x dx, and I don't see that anywhere in the integral, so we're stuck there too. And for this, you're supposed to think, well, there's this other way that I could write cotangent. Cotangent x dx, well, that's the same as, if tangent is sine over cosine, well, then cotangent is cosine over sine. And that's a bit of a theme here with the trig functions. If you pick u to be sine x, well, you better have a cosine x in the integral. If you pick u to be cosine, you better have a sine x in the integral. And we have both here. We want to pick u to be sine x so that we can get 1 over u du. If you pick u to be cosine, then you're going to have that sine x in the denominator, which is really a cosecant. Remember, because 1 over sine is cosecant. So it can only be done one way, it's not interchangeable, so you do need to pick u to be sine x. Then du, well, that's cosine x dx. And so then this integral here converts into 1 over u by design, because I picked u to be sine x. Then I have the cosine x dx left over to account for, and guess what? That's equal to exactly du. I'm very good at this integral. It's ln absolute value of u plus c. And then u was equal to sine x. Now there's some issues there with the ln of sine x, because ln, it's ln of that. That's why you have to have absolute value, because ln cannot, you're not allowed to put anything negative into an ln. It's not defined for values less than 0 or even equal to 0. And so you do have issues when sine x equals 0 here, which aren't really addressed in the problem, but you did originally anyway. But here you definitely need the absolute value around that. Okay, so that's the answer. Make sure I don't need to do another equals. Okay, that's a good one for you to do yourself. Do it over and over until you can do the whole thing by yourself without looking. That's good. And I think example 6 actually is better to do that with. Oh, hold on. Do I have a... no. That's all fine. That's all fine. Example 6 has a little extra goodie in there because you pick u to be cosine, and then when you take the derivative, you get a minus. So there's a little extra thing to do there for tangent. I recommend doing that. Example 6. Okay, number 42. I'm going to make this the last one. Number 42. Number 42 says, look at that. He's really reaching now. We got sine t, and then I've got secant squared. What does that remind you of? But it's secant squared of cosine t. Boy, that's rigged. You see the cosine there? If you pick u to be cosine, you got the du sitting right there. And on top of that, this is an integral that's well known to us. The antiderivative of secant squared is equal to tangent. So That's what I see here. With all this gobbledygook, I say, let's let u equal cosine t. Then du is minus sine t dt. I go to substitute. I'm not afraid of secant squared u. That's what I have here, right? Because u is cosine. Then I have secant squared, and I still have the sine dt, sine t dt to substitute. And look, it's right here. That's equal to minus du. So minus du. I'm really good at that integral. That's minus tangent of u. And then put in what u is. U is equal to cosine. So minus tangent of cosine t plus c. There you go. Okay, that's enough of that. We will pick up the next live stream on number 43.